we talked about different stages in developing and implementing a relational database, right? So we wanted to start from scratch, from like defining our requirements, the objectives, and what are the rules that we want to define, what is the scope of our project. So we started with that first step. And then what was the second one? After we collected all the requirements, defined our business rules and assumptions, what was the next step? Anyone?
Sorry, can you
yeah, so we started with, we were talking about different stages in designing and developing a database, right? A relational database. So step one was collecting the requirements and defining your business rules, assumptions. This is what you're doing in your project, right? Also in assignment 1. So these are the requirements. So here you define, for example, what is the business objective, what is the scope of your project, and then you define your rules. What are the business rules? What are the assumptions? Can you give me an example of a rule? For like our famous example of a student registration.
The student can be enrolled in many classes.
Yeah, so the relationship, so when I talk about business rules, I mean different entities that you have that you will include later in your model, plus its attributes, plus the relationship between those entities. So these are your business rules. For example, say, okay, we have student, course, enrollment, instructor, and so on. And what are the rules? Each student can enroll in multiple courses, right? Each course can have one or more enrollments. Or for example, one course can be taught, for example, by only one instructor, right? But each instructor can teach 0 or multiple courses, and so on. So you define the relationships, and so that is for this stage. And then we had ER modeling, right? And in this stage, we just draw whatever we defined in the previous one, right? For example, you wrote here, what was your rule? You say student can enroll in 1 or more courses, and each course can have 1 or more students enrolled in it, right? So here you have the student and you have the course, right? And then you have this many-to-many relationship that you also learned. You have to convert it to what? When you have a many-to-many relationship, what do you do? Associative entity, right? Composite entity or associative entity. You use it to convert this many-to-many relationship into two one-to-many relationship, right? So this will be a composite entity then. And here you have a one-to-many relationship, and here also you have a one-to-many, right? This way, instead of saying the student enroll in multiple courses and each course have many students enrolled in it, we define this relationship between a student and enrollment, right? And also course and enrollment. So this is a one-to-many, this is also one-to-many. So here, say each student can have multiple enrollments, right? So this should be like this. So each student can have multiple enrollment, but each enrollment is specifically for one student, right? And vice versa. So each course can be appeared in multiple enrollments, but each enrollment belongs to only one course. So this is what we have covered so far, right? And we also learned how to convert this into a relational schema. So we said each of like these entities are going to be what in your database later? Tables, right? And we also had some attributes here. For example, we have a student ID, which is a unique identifier. We have a student full name, What is the type of name? What type of attribute is it? What type of attribute is name? Multi-valued? Yes? Composite attribute. Why? It's composed of first name, last name, right? Similar to address. So first name, last name. So we also learned about different types of attributes, right? So what these attributes gonna be in your relational schema? Are they going to be tables? Columns of your tables, right? So you will have a student table with all these attributes as the columns. So you will have a student ID 1 column, first name, last name, email, and so on. And how do you show the relationship? So here we show the relationship like this. How do you show the relationship in your real database then? How can we see, for example, a student table, for example, is connected to enrollment?
So I think conceptual or like you have like a diagram as well.
You're right, but not the answer of this question. Yeah.
In the enrollment table, would there be a foreign key related to the student?
Exactly, foreign keys. Foreign keys is what relating tables together, right? So we said that in order to connect the tables together or link them together, we need a common attribute between two tables, right? So what is a common attribute? That's a primary key of one table appearing as a foreign key in the other table, right? So for instance here, you will have a student ID, which is it a primary key in the enrollment table? What is it? Foreign key, right? Why is it a foreign key? Because it was a primary key in the student table, and now we are using it to link the enrollment table to the student table, right? Similarly, we have course ID here as the primary key, right? Because this is the unique identifier here. And we have course name and so on. And so here, we also have course ID, which is again foreign key, right? This time, this foreign key is used to link the enrollment table to the course table, right? Because we want to see, for example, for each enrollment was related, to which course, right? So this will be your, for example, relational schema. So here you have a student table, a student ID, first name, last name, right? And this is your primary key. And then we have the enrollment table with, again, a student ID and course ID. Each of them alone are foreign keys in the enrollment table, whereas together they form a primary key, composite primary key, right? And what is a composite primary key?
Primary.
Someone else. Composite primary key. That's easy.
Group of columns forming one primary key.
Yeah, group of columns forming a primary key. Because primary key is not always just one column. So here, a student ID and course ID together, this is your composite primary key, right? Each of them alone are foreign keys because they're used to link the enrollment table to a student and course table, right? And this is your course table. And here you have course ID, this is primary key here, course name, maybe description, instructor ID, and so on, right? Okay, so this is what we've learned so far. So first of all, what is normalization? So this is the process of actually breaking down a big table into multiple smaller tables. And why do we need that? So let me just to clarify this with an example. So suppose you want to store data for, back again to our example, I would like to be consistent with this example. A student registration, right? Now, in a student registration, I create a table and then I'll ask you what's the problem with this, okay? So, I'm trying to write here to so that it's going to be shown in the recording. So here I have, let's say, student ID, a student name, and course ID, course name, instructor ID, instructor name, maybe instructor office, and so on. So student ID 1, for example, is Mona. Course ID is 3421, which is the database, and it's taught by, Dr. Brown. Sorry, the ID is, 100. Brown office is, last one. So I put everything in one table, right? So what is the problem with this? Redundancy, and can you further elaborate on that?
Like for example, we just designing a database for a bookstore, and we just put like for example book name, and for example like the authors. When we put authors, so we can put like multiple authors' name, which is for one book, and there's the author name, book name, like publisher, everything. So this is a big table, and there's a lot of redundancy and reputations there. So we can divide it into two tables: the authors and the book, or the authors and the book, and then we can just put authors, book name, and then that way it's not going to be repeated.
Right. Yeah. Okay. Redundancy is one issue, and how does it cause problems later? For instance, if you want to insert data later, if you want to update some data, or if you even want to delete some data, think about how this design can cause a problem. And this will also help you when you want to build your databases for your project. Because it may seem easy when we are just showing you tables like the normalized tables, but when you actually go and think about it yourself, okay, what I have to put in one table? And why not, for example, putting instructor name along with the student? For example, if I have a student table, why I cannot have a student ID, student name, instructor ID, instructor name? What's the problem with that? And how to decompose these tables, how to break down this big table into separate tables. So we know that this causes redundancy. How do we know how many tables do we need to normalize this table, to ensure data integrity, and to ensure that there will be no anomalies later? And what do I mean by anomalies? So we have three types of anomalies: insertion, update, and delete anomaly, okay? So let's see with an example what do they mean. For example, here is similar to the table I created, right? We put everything in one table. We have student ID, student name, course ID, instructor, and so on. So can you give me an example of an anomaly, like insert, update, or delete, or anything here?
If you delete the name, I think you need to delete the rest.
So the problem is when you want to delete like a value in a specific attribute, in a specific column, right? The way that it works in SQL, you are deleting the row, right? And so, for example, if you delete, for example, instructor Mona, you may lose all other information as well. For example, the course information and so on. Or if you, for example, want to update some information, let's say, for example, you want to update Dr. Brown's office. So here we have redundancy, as your friend said, And what is the problem with redundancy? Now, this is just a very small table just to show you as an example. But in real world, like imagine you have a table with like millions of rows where you have hundreds of rows like repeating, redundant data. Why? Because maybe Dr. Brown is teaching 100 courses, okay? And so the problem that it causes is, for example, if you want to like update Dr. Brown's office, then you have to update all those rows. Instead of just one row, you have to update all the rows where the instructor is Dr. Brown, right? And isn't it inefficient? And what if there were some, like, let's say, issues in your database? Like, if the data was manually entered, or, like, for example, somewhere Dr. Brown have some extra space. So you miss updating that, right? Because you're updating wherever instructor name is Dr. Brown. And if you have a typo in just a few of those rows or one row, then you will miss updating them. So it's not efficient, right? And we agree that this doesn't work because of update anomaly, because of insertion and deletion anomalies. So we are going to see different examples here. For example, let's say you want to enter a new course. And this is just we design a new course, for example, for EECS department, and we have not yet decided who is going to be the instructor. So the instructor is going to be null, right? And so also there has been no student yet enrolled in that course because it's just a new course that we designed. Or, for example, another example of a deletion anomaly. So if a student drop a course, we lose the course and instructor detail as well, right? The same, if you, for example, delete an instructor, you again lose all other information, especially if that instructor is teaching only one course. Then when you delete like that and no other instructor is teaching that course, so let's say I'm the only one teaching database, right? And then if you delete me from the database, from your table, then you will lose all the information about the database course as well, right? Maybe you want to see what is the course description, what is the credit of the course, and so on, and you will lose that information. So this is not efficient. And what if Dr. Brown wants to change his office? I already explained, right? Then you have to update multiple rows instead of one. So how normalization prevent this? So now think about how to normalize this table. And by normalizing, I mean putting like the attributes in separate tables in a way that later, if you want to, for example, do updates, insert new data, and so on, these problems that we explained do not happen. How do you do that?
I can create like 3 tables.
Create 3 tables. Yep, you. Yes.
3 separate tables. Student,
Why?
because if you delete the ID, it means the student doesn't exist.
Yes. Okay, so we will have 3 separate tables, one for course, one for instructor, and one for student, right? And like later for other examples, if they look complicated to you, you can think of like each table representing, you need at least one table to represent each entity, right? Each main object or concept in your database. For example, what do I mean by entity? Like a person, right? Or like an employee, student, something like that, doctors. So if you're, for example, designing the database for a hospital, what are your entities or objects? Some of the example, object could be anything, a place, a person, right? For which you want to keep track of the data, right? For example, you want to keep track of information of the patients, right? So you have to have a table for patient. You have to have tables for doctors because you may want to see, for example, what are different like doctors' specialty, right? And you look at me a bit confused. Am I talking clear? It's clear. Do you have any questions?
If I was to make another table for the like office, like the possible offices, would that be too far or no?
If you create table for?
You know how like there's instructor office, like office 101, office 102? I feel like that would be a different entity, or is it okay to keep it in the same table as?
You mean having different entity for offices?
Yeah.
It depends. No, it's not a strange. It depends on how much detailed information you want to keep about each thing, right? If it's just like different offices want to be as some attributes for instructors so that you just keep track of where each instructor office is, then why like having another entity? But if you want to have, for example, more detailed information, like for example, what are the equipments in each office, where each office is located, or many other information, especially if this is if it's a, for example, office is a classroom, then you may have even more attributes for that. So you want to have a table for an entity for which you have at least some meaningful attributes, and later you want to retrieve like data from that table frequently. Otherwise, it is not necessary, right? Just like getting some extra space, and it's redundant. And we also learn later in this class, not this class, but this course, that not always we want to normalize tables. Sometimes we want to denormalize tables. We actually intentionally want to denormalize tables. And that's just for now. You can think of it as when you only want to, for example, want the data for reporting or analysis purposes. You don't have, it's mainly for read purposes. And the performance, the read performance is more important for you rather than update. For example, if you don't have many updates, frequent updates in your tables, if you are, for example, working with data warehouses, keeping like historical information, in those like rare cases, rare in this class, we may also want to denormalize. But the focus of this session is when we want to normalize tables, which is the case where with most OLTP applications or online transaction processing applications, when the writing performance is more important, when you have lots of updates in your tables, when the data are frequently updated, right? In that case, we want to normalize tables. And so, do you think of the fourth table that we may need here? And by the way, this slide, this is not complete. This is just to address one problem. So to fully normalize this table, as your friend suggested, we need like 3 tables, right? Course, instructor, and a student. Can you think of a 4th table that we need?
Maybe address?
I'm sorry, yeah.
Enrollment?
Enrollment, right? We also want to have enrollment because a student and course, like we know, have many-to-many relationship, and we need an enrollment table. So, problem with this table. You cannot see this. So we have a table with first name, last name, email. That's for students, and their advisor name, department, and advisor admin last name. So can you tell me what are the problems with this table? You can, if this is like too small, you can check it in your slide. So who can tell me what are the problems? Anyone else? It's fine, like you don't lose anything if you say something that is not correct, right? I do it most of the times.
There's like different categories that don't relate to each other.
Sorry?
There's different categories that don't relate to each other, like the advisor and like.
Yeah. So, like in other words, there are like different entities here, right? And we'll have like these anomalies later that we'll discuss. Yes. Exactly. Yeah. If a student changed the advisor, for example, let's say Andrew changed his advisor. So Andrew's advisor is Baker right now, right? So if he changed advisor to Valdez, what happens? What other fields we have to update? Not only advisor last name, but also email, advisor email, even the department, right? Because the previous advisor department was accounting, whereas the new advisor is chemistry.
And the last name as well.
Exactly. So there are different fields that then we have to update. So here you see, for example, Matthew changes advisor to, let's say, another advisor, Tang. Then we need to update advisor email as well. And in this case, you don't need to update the department, right? Because they are both from the accounting. And what if you delete a student, like, for example, Marino, right? And if you delete this student, what happens?
The other data will be lost.
Yeah, you have this here. The advisor and department information will be lost. And what if you insert a new department for which we still do not have any information, right? So we cannot insert a new department, for example, biology, because both the student and advisor data are missing. And this is just another example. Now, a very important concept from this topic, you will have questions in your exam, midterm, final exam. You have it in your assignment. So I cannot emphasize enough how important it is. Because if you don't understand the functional dependencies, then it would be very difficult for you to normalize tables, okay? So the boring part, the definition, given a relation or a table, right? The attribute y is functionally dependent on attribute x. So just be careful. When we say y is dependent on x, we write it this way. So this means y depends on x, or x can uniquely identify or determine y. So we say y is functionally dependent on x if and only if whenever two tuples of R agree on their x value, they must necessarily agree on their y value. And I will explain, don't worry. And when the value of one or more columns in each row of a table uniquely identify the value of another column in the same row of that table. So let's see what do I mean with that. So here we have a student ID, a student name, course ID, course title, and grade. So I can say a student ID is functionally dependent on, a student name is functionally dependent on a student ID. Is that correct? And what do I mean by that? I mean a student ID can uniquely identify a student name. And what does that mean? That means for each student ID, we only have one student name, right? We cannot have two. So go back to the previous slide and read it again. So when the value of one or more columns in each row of a table uniquely identify the value of another column, right? That is, for example, each value in a student ID can uniquely identify each value in a student name. Because each student ID is unique, right? It's specifically for one student. And it's always true for all primary keys, right? Because all the primary keys in tables can uniquely identify each row. So all other columns in the table, they all are functionally dependent on the primary key, right? Or primary key can uniquely identify all other columns. So if this is, for example, primary key, then this could be all other columns, right? And we'll see more examples. So it's easy to find the functional dependency between primary key and other columns because we already explained that primary key uniquely identify all other columns. What about the other ones? Then you have to use more logic and critical thinking. So for example, can course title uniquely identify a student name? No. Why? You have to ask this question. Can each course title uniquely identify student name. That is, for each course title, do we have only one student name? No. For each course ID, do we have only one course title, a specific course title? Yes. Student ID and grade. Does a student ID uniquely identify its grade? No. Could be for different courses, right? You cannot, like having a student ID alone, you cannot identify the grade, right? Because grade on which course? Course ID and grade. Can course ID uniquely identify a grade? Yes. Again, no, because
there will be same course for that. So course ID is allotted to one particular course, which then has the grade for that particular student.
For that particular student. But do we have a student here? Yeah, so course ID alone, you're right. A student ID and course ID together, right? A student ID and course ID together can identify the grade. And that's easy if you think a student ID and course ID are primary key of the enrollment table, right? Together, that's a primary key. And primary key always identify all other columns because by definition, primary key can uniquely identify each row in a table, right? Am I correct? Are you bored? No? Tired? Sleepy? And what time is it? 12. I'm going to give you a break soon at maybe like in 20 minutes. I give you a break in 20 minutes, so just tolerate me a little more. Yeah.
Can you say student ID is dependent on student name or the other?
Yeah, that's important. A student ID can uniquely identify student name, meaning a student name is dependent on a student ID. A student ID doesn't depend on a student name, right? So this means X uniquely determine or identify Y, or Y is functionally dependent on X. Okay, is this clear? So this is the way you read it. And here you see, for example, student ID alone cannot uniquely identify grade, as you see Susan Water, right? Have different grades. So having a student ID, for example, whatever this ID is for this student, it couldn't uniquely identify, that is, for each instance of this, we do not have a unique equal instance in the grade, right? We have different instances. We have A and A+.
For the page number, but for functional dependence, slide 1, I just don't understand the first one.
Here?
Yeah, that one.
So it says what I already explained here. If you have a table with like 2 columns, right? And we say, for example, this column is functionally dependent on this one. If for each instance of this, you have only one instance of this. For example, for each student ID, we only have one student name. For each course ID, we only have one course title, right? That, for example, we know that the primary keys can uniquely identify each row, right? What does that mean? That means, for example, in a student table, a student ID is unique because each student have a unique student ID, right? And so if that's the case, it means that for each student ID, like each student ID, can belong to only one student name, one student email, and so on, right?
So it's basically the same thing for the, like what you wrote. X uniquely determines Y, and Y is functionally dependent on X. It's the same thing.
Yes, yeah. But I want you to know the difference when I say, for example, X uniquely determine Y, I write it this way. So it doesn't mean Y uniquely identify X, right? That is not correct. So either you, like when I write this, either you read it this way, X can uniquely identify Y, or Y is functionally dependent on X. Yeah.
Could you just quickly go to the next slide?
Yeah.
So we covered like student ID and student name, course ID and the course title, and how like the names in both cases are functionally dependent on the ID.
Mm-hmm.
But if we're referring to the grade, would it be wrong to say that the grade is functionally dependent on student ID and course ID?
No, this is correct. Yeah. Grade is functionally dependent on both because student ID and course ID together are primary keys, composite primary key, right? And they uniquely identify grade. And now, another important thing, I want to talk about different normal forms and different types of dependency. So we have different types of dependency. We have also different normalized form. And I would like you to only learn 3 normal forms for this class. So first normal form, second normal form, and third normal form. So we call them 1NF, 2NF, or second normal form, and 3NF, or third normal form. So what is the first normal form? First normal form means that, like you say, a table is in 1NF if there is no, for example, multiple values stored in one cell, or you have no repeated data, right? So a table is in 1NF if each record is unique, that is, you don't have duplicated records, right? And no column in any rows contain multiple values, that is, no repeated groups. That's against the atomicity, right? Do you remember when I was talking about atomic values? I mentioned we cannot store multiple values in one cell. So even if you have a multi-valued attribute in your design, which is fine, in your ER model, you design phone number as a multi-valued attribute. But you cannot have that as like an attribute in your table later. For example, if here you have this student entity and you have phone number, right? You have phone number as multi-valued attribute, right? Later when you want to convert it into your like tables, you have a student table, and we said all these attributes, like for example, a student ID, name, and so on, will be your columns, right? So student ID, name, and so on will be your columns. But we cannot have phone number here with like multiple numbers. So this is not correct, right? How do we overcome that problem? One way of designing base when you have a multi-valued attribute, one way is to design a separate table for that, okay? So you have, for example, and please do not confuse multi-valued attributes with something that could be this or that, for example, true or false. Because if a column can get, for example, you have a column that only accepts true, false, yes, no, right? It is not multi-valued because it's either yes or no. It is either true or false, right? That means, yeah, so you cannot have true and false at the same time stored in one cell. You cannot have yes and no at the same time stored in one cell, right? What are other examples of multi-valued rather than phone number? Maybe for the course, the days that, for example, that a course can have, like for example, Monday and Wednesday, right? At the same time, you can have Monday and Wednesday for one course, right? Because that course is 2 days per week, Monday, Wednesday. You cannot store that in one cell. So multi-valued means having like more than one value at the same time, like a person having different phone numbers, right? In that case, if that's the case, you design it in just a separate table, okay? And back to the first normal form. So no duplicated rows and no multiple values in any cell. That is 1NF. Simple, right? And most of the tables that we had so far, that you have seen so far, were already in 1NF. And I'm going to show you tables that are not in 1NF.
What if we make phone number as two attributes, phone number 1 and phone number 2? Can we still have it in the same table?
That is possible if you have, that is another design. It's just for phone number if that's only like 2 phone numbers.
But
yeah.
It takes more space if we like make to it.
It depends. For example, if you are going, for example, to constantly storing, like for example, retrieving data from a separate, like for just phone numbers later, then having a separate table makes sense. If you have lots of queries later dealing with that phone number, right? Because then you are only dealing with that one table with only one, let's say two columns. That is like, for example, a student ID and phone number. Rather than like a table that have many columns, right? And then every time you're updating all the rows and all the columns because of just that phone number. Is that clear? And so 1NF means atomic values, right? Now, let's look at these tables. And I'm going to zoom a little bit here. So in the table, like on the top, we have a student ID name, campus address, major, course ID, title, instructor. So basically the table that we initially had, like putting everything in one table, right? And so is this table in 1NF? Why it is not in 1NF?
Because there are two course IDs, two different course titles.
Yeah, so we are storing multiple, for example, course titles and course IDs for one student. That is the problem that we discussed last session, right? We said when we have, for example, many-to-many relationship, right? So for example, for each student, we can have, like each student can enroll in multiple courses. So, and for each course, again, we have multiple students enrolled in it. So if you're going to like not having separate tables and do not use normalization, then you will come up with these issues. Then you have to store data somewhere, right? So you're going to put all the like course IDs and course titles in one cell, and that's not efficient. What's the problem with this? What's the problem if I just want to put that? That's easy. Just writing all the courses that the student take in one. Deleting cause problems, right? So how do you delete? And that's for that you need to understand how in SQL you are actually deleting, for example, or updating rows. For example, if you want to delete database management from your database, okay? So you want to delete that course, that specific course. Now, it doesn't delete a word, so it doesn't work with a string match. You can write queries with like having a string match in SQL. That's not efficient though, right? And that's only one problem. It causes other problems too. So if you delete database management, you will lose also other courses, right? Because that deletes everything that is in that cell, right? Or if you update information, how can you update that? For example, you want to update, I don't know, instructor for system analysis, right? So if you want to update instructor for system analysis course, when you want to write the query, you write, for example, update this table, and you have to add a condition, right? And the condition is where course title is system analysis. And we don't have that. The course title here in the first row is database management system analysis. It's not system analysis alone. Unless you use like string matching, which is out of scope of this class and is not also efficient for designing your like relational databases. So we want to have them, like keep them atomic, right? Having only one value in each cell. So this is not first normal form. And so here, it separated these like table into two tables. One for student information, right? And the other one for storing the course information, right? So this one, you have, for example, and this student ID here, is it primary key or foreign key? Is a student ID in the table on the bottom right primary key or foreign key? Foreign key. Why? Yeah, a student ID is primary key in the student table because a student ID can uniquely identify students in a student table, right? But not in this table. Here we can have, as you can see, a student ID is not unique. The first and second row, right, belong to the same student because that student took multiple courses. Again, row number 3, 4, 5, right, are for like the same student who took 3 courses: database management, fund accounting, fundamental accounting, introduction to something, right? So these are like different. And what is the primary key here in the table on the bottom right? Someone else, someone from this side of the class. What is the primary key in the bottom row? In the bottom right.
Course ID.
Sorry?
Course ID.
Course ID. And then ask yourself, is the course ID unique in this table? No. So what is the primary key here? Primary key is a column or combination of columns that can uniquely identify each row. So if I'm asking you, or if you're looking for a primary key in each table, look at like the columns, right? And see which of those columns in the table can uniquely identify each row, right? Student ID, is it unique? No. Course ID? No. Course title? No. Instructor name? No. And so on, right? Now, let's look at the combination of columns. Course ID, student ID can uniquely identify, right? So that's your primary key, and it's a composite primary key. Okay, and now, okay, so for the first normal form, and that I already explained, student ID is your primary key with course ID. And so this is just an explanation of what you do if a table is not in 1NF and you want to make it in 1NF. So that is, if you have multiple values stored in a cell, you have like different ways to do it, to deal with it, right? You either store them in different columns or you store them in different rows, right? In this case, we wanted to have them in different rows because for each student, we wanted to show which courses it takes. Now 2NF. So 2NF means that it's already in 1NF plus, so you have to be careful. So as they go down, they always have to have the conditions of the previous ones as well. So for example, for a table to be 2NF, should already be in 1NF plus some extra requirements. 3NF means 2NF. That means the table is 1NF, 2NF, right? Plus some requirements. Now, what are the requirements for 2NF? No partial dependency. And I'm going to explain the dependencies. So, no partial dependency. For 3NF, there should be no transitive dependency. Now, the only thing that you have to learn is what is partial dependency and what is transitive dependency. If you learn that well, then you know you can identify the normal forms, right? And then you can better understand how to normalize tables. For example, if I give you a table and ask you, normalize it until 2NF. So you know that you should have no partial dependency to be in 2NF. You can still have transitive dependency, right? Or if I ask you to normalize a table until 3NF or third normal form, it means that not only you don't have you don't have to have any partial dependency, but also you do not have to have any transitive dependency. Now let's see what are like these dependencies. Okay, partial dependency means you have a column that depends only on part of your primary key and not all your primary key. And what does that mean? So for example, let's say you have a table enrollment, right? Enrollment has composite primary key, right? What is the primary key of enrollment? A student ID, course ID, right? A student ID, course ID. And so we have something like this. A student ID, course ID, and grade. And so this is one example. Let's say we also have a student name here. Okay. So by definition, I said partial dependency means when a column in a table depends on only part of your primary key. So it means, for example, here, does grade, what is your primary key? Student ID and course ID, right? So that is your primary key. Now, is grade partially dependent on primary key here? What does that mean? Does grade depend on student ID only? Or does grade depend on course ID only? Can a student ID alone uniquely identify grade? Or can course ID alone uniquely identify grade? No, we explained that is not correct because, for example, we have a student ID, let's say 10, right? And this is, I don't know, Alex, right? Is taking different courses like database and AI course with different grades, A and B+, right? Now, did a student ID uniquely, did a student ID uniquely identified grade? No, because for the same student ID, you have different grades, right? So it didn't uniquely identify that. Now for course ID, does course ID uniquely identify grade?
Yes.
I like that. Why?
It's unique.
But
It's not repeat.
could it be always unique? Like if I add another student, I don't know, student ID 5
It's dependent on
for course ID database, because this course can have multiple students enrolled in that course, and this student is, I don't know, John, right? And this student took, for example, got A, right? Or another grade. So you see what is the problem, right? So course ID alone cannot, I don't know, let's put another grade, C. So course ID alone cannot uniquely identify grade because we have two same courses, right? With different grades. So it's not like whenever you say database, you know what is the grade, right? So you have to ask yourself this. For example, when I say course ID can uniquely identify course name, that's because if I say 3421, what do you respond? Database, right? 3401, AI. 4412, data mining. So whatever course ID that I name, you can tell what is the course name, right? Now, if I tell you different student IDs, if I tell you your student number, that's only you, right? Only one student. But if I say, for example, 3421, can you tell me the grade? No. There are many students taking 3421 with different grades. So with this course, different students, different grades, right? Even if in this like a small table that I show you, even if in that small table, let's say this is the case, okay? Still, like even if now you think that course ID can uniquely identify grade, that's not true because later you have to think like more broad, right? later you may have another student in the same course with another grade. And it's very rare that all students in the same course take the same grade. Is that possible? Like all of you getting like A. That's not possible. So this is not partial dependency. There is no partial dependency between grade and, for example, course ID or a student ID. Can you find a partial dependency in this table?
Student name and student ID.
A student name and a student ID, perfect, right? A student ID can uniquely identify a student name. Whatever student ID I tell you, you can give me who is the student. And because course ID, which is part of your primary key, cannot uniquely identify a student name, right? That means student name only depends on part of your primary key. Your primary key is a student ID and course ID, right? This is your primary key. And a student name only depends on a student ID, right? And because it depends on only part of your primary key, we call it partial dependency, okay? Now, a question. Can we say that all the tables that have composite primary key, have partial dependency? Why?
You can always move any partial dependencies to a different table.
Yeah, but let's say we have. Like, is it like, does that imply if we have a partial, no. Because your table could look like a student ID, course ID, grade, right? And that's the correct design of 3NF, right? If we have course ID, student ID, and grade, we have a table with composite primary key, right? But do we have partial dependency then? No, we don't have. So if a table has a composite primary key, you always look for partial dependency. You may find it or you may not find it, okay? Now, another question. If a table, can we say, there are 2 points that I want you to remember. First is that if we have a composite primary key, it means that it's just a hint that you look for it, right? But what if we don't have a composite primary key? Can we have a table with single primary key, but with partial dependency? Can we have a table, can you give me an example of a table without composite primary key or with single primary key that have partial dependency?
Maybe if the table has like 2 primary keys and 2 different entities.
If the table has 2 primary key, what does that mean?
2 entities.
2 entities means 2 tables.
I know, but what if it's in one table and then the other side?
So if you have one table with 2 primary keys, is that possible? Can we have a table with 2 primary keys? So primary key is a column that can uniquely identify. I think I know what you mean. We can have table with multiple columns identified as primary key, but they together form a composite primary key, right? For example, here we have 2 columns as primary key, right? But both of them together. So we have 1 primary key. Always, each table has only 1 primary key, 1 unique identifier. Now that 1 primary key can be only 1 column or can be more than 2 columns, right? So we have a table that 1 or more columns can form a primary key. If more than 1 column is primary key, that's a composite primary key. Now my question is, we have a table with single primary key. We have this table here, and this is our primary key here, single column primary key. Can we have a partial dependency? It is not possible, right? Because how can you? Like, it's by definition, we say partial dependency means if a column in your table, you have some column here, right? If a column in a table depends on part of primary key. So if your primary key only has one part, either it's dependent on that part or not, right? You don't have several parts that is dependent only on part of it. That's why I said, when I give you a table and I ask you for what are the dependencies in this table, look at the primary key first, okay? So if primary key is composite primary key, then you have to look for partial dependency. You may find it or you may not, okay? But if you don't have a composite primary key, and if it's just single primary key, instantly say it's 2NF, because there is no way that it can have a partial dependency, right? And that's easy. So 1NF, that is no multiple values in any cell, no duplicates, plus no partial dependency means 2NF. And I can also tell you this, just so that you remember. So if a table has composite primary key, composite primary key means more than one column form a primary key. But primary key is always one, right? So if a table has composite primary key, you may or may not have partial dependency. So if you have a composite primary key, search for it, look for it. But if a table do not have composite primary key, no partial dependency. Okay? And if a table has no composite primary key, means having no partial dependency, and if it's already in 1NF, you say instantly that it's in 2NF, right? So this means that it's 2NF. Now let's look for what is transitive dependency. So transitive dependency means, and I promise I give you a break as soon as I finish transitive dependency. So transitive dependency means you have two columns or more, and one column depends on another, but like it's the same as what we have covered so far, but none of them are primary keys. The definition says when a non-key column can uniquely identify another non-key column, but I would like to note that by non-key column, it means like in your textbook or like online, you may see this definition when a non-key column uniquely identify another non-key. By non-key, it only means primary key. The column can still be a foreign key, okay? And when we call non-key, it means that non-primary key. Now, so the same way that we had here, a student ID can uniquely identify student course. So a student name. So a student name is dependent on a student ID, right? And we call it a full dependency or like just normal functional dependency. Partial dependency, if you have a composite primary key and there is a column somewhere like a student name that depends only on part of your primary key, like a student ID in the enrollment table, right? Because in the enrollment table, you have composite primary key. And then if you have a student name, that means your table is not still normalized, right? That's not a normalized table. So you have a student name also in the enrollment table. You know that, oh, yeah, we have composite primary key. We have like this partial dependency between a student name and part of primary key, which is a student ID. So it is not in 2NF, right? And because it is not in 2NF, the table needs normalization. If I ask you to normalize it to 2NF, then you know that you have to get rid of that dependency. Now, transitive dependency, the same. It's just between non-key columns, okay? Let's see some examples. So here is just for second normal form. So as you see, for example, we have A and B as your primary key, okay? And then, for example, let's say A and B determine C. For example, a student ID and course ID uniquely identify grade, right? That's a full key dependency, right? It's not partial. We call it full key dependency. So that's no partial dependency. And if B, let's say, for example, course ID, and D is course name, then course name is only dependent on course ID, which is part of your primary key, right? So if D is only dependent on B, is that partial dependency? Hello? Is that? Yes. That is partial dependency. And how do you normalize such table? So if you have a table with that situation, like a student ID, course ID, and let's say a student name and grade. So is this in 2NF? No, because your primary key is this, which is composite primary key. If you have composite primary key, you look for partial dependency. Maybe you have. Do we have partial dependency here? Yes, between student name and a student ID, right? This is your partial dependency. How do you normalize this table? Get rid of partial dependency, okay? That's why dependencies are important. Because if I give you a table asking you to normalize it, you have to first find the dependencies. So if there is a partial dependency, it means the table is not even in 2NF, right? If a table is not in 2NF, can it be in 3NF? No. Right? So how do we normalize this?
Remove this first
Get rid of this dependency. So the student name here is the problem. So we need a separate table. So here we only keep a student ID, course ID, and grade, right? This is okay, no problem, because this is your primary key, which is composite. We have a composite primary key, and as I said, when you have a composite primary key, you mean maybe you have or maybe you not have partial dependency. In this case, we don't have partial dependency. And grade depends on both of them, so it means full key dependency. We have no problem with full key dependency. That's the perfect normal form, okay? No partial, so it's already in 2NF, right? And let's put a student name in another table, which is a student information, right? So that is how you normalize tables. So here is another example, which we already discussed for second normal form. So the dependencies here are shown. Like, for example, the table on the top is enrollment table, right? We have a student ID and course ID together, so it's enrollment. Is it a normalized table? Is it like in 2NF? It's not 2NF. We have a composite primary key, right? And we also have partial dependency. What are the partial dependencies here? Course title and course ID. Is that a partial dependency? Yes.
Yeah.
And how do you normalize this table? Get rid of the dependencies, right? And break it down. So back to the very first slide about normalization. Do you remember the definition of normalization that I skipped at that time because I wanted you to read example. So it means breaking down a big table into multiple tables to avoid redundancy and ensure consistency of your data, right? So that's what normalization does. Get rid of like all those dependencies. So here we have one student, one enrollment table, and one table with course and instructor. Now look at the table on the bottom left. A student ID, course ID, grade. Is this table in 2NF? Yes. Okay. It's also in 3NF, but we didn't discuss it yet, so keep it here for now. What about table on the bottom right, the red one? Which normal form is it? Is it in first normal form? Yes. Why? no repetition, right? No duplicated records, no, like, and there is all atomic values, that is no multiple values in one cell, so that is 1NF. Is it in 2NF?
Yes.
Because it's already in 1NF and there is no partial dependency. And you, like, for this table, you have to tell me like it's in 2NF in 1 second, because it's a single primary key. And when it's a single primary key, like, instantly you say 2NF, right? There is no possibility of having partial dependency. And is the table in 3NF? 3NF means no transitive dependency. Transitive dependency means there is a dependency between two non-key columns. Can you find some non-key columns in this table, the red one on the bottom right, that are dependent on each other? Yes? Sorry?
Instructor name and instructor location?
Yeah. Instructor location depends on instructor name, right? Because each instructor has a specific office, right? And so instructor name can uniquely identify instructor office. Are these two columns key? No. Like in this table, they are not primary key, they are not foreign key, they're nothing, right? Even if they were foreign keys, we don't care. We only care about primary key when we talk about dependencies. So, second normal form, this is how you do it. And you want to remove partial dependency. And we already explained how do we do that, right? And you can think of it as putting all the attributes that are relevant to an entity in one table. Most of the time, for example, for a student table, is everything related, all attributes related to the student, right? Student ID, student name, student email, address, so on. For course, everything about course entity, course ID, course name, course description, so on. For instructor, the same. But we have sometimes some tables like enrollment that were associative entities before, so they have more attributes from other tables. They represent foreign keys, right? We have foreign keys in tables because we want to link them together. So you may have, for example, in the course table, you may also have just instructor ID, right? And that's no problem. If you only have, for example, here, if you have the course table with course ID, course name, and only instructor ID. First of all, this is a course table. What is the primary key? Course ID, right? Course ID can uniquely identify each course in the course table. What is the instructor ID in this table? Foreign key, right? Because instructor ID, this is going to be linked to the instructor table, right? So that later, name, maybe office, and so on. So this is a foreign key because it's primary key in the instructor table, and that's to link these two tables, because maybe we want to see, for example, what is the name of an instructor of a specific course, right? And only accessing or querying this table doesn't give us the answer, right? Because we want the name. So we link these two tables through instructor ID to give the instructor name or office or so on. And so, what was I talking about? I lost. So we remove partial dependencies to be in 2NF or 3NF. If you remove partial dependencies, which normal form is guaranteed? If you remove partial dependency, 2NF is guaranteed, right? Because you may still have transitive dependencies, right? What if you get rid of both partial dependencies and transitive dependencies? Then you are in 3NF. That means here, in the table on the bottom right, you already got rid of partial dependencies, and it's in 2NF, but you have not got rid of the transitive dependencies yet, right? You still have instructor information in the course table. How do you further break down this table into more tables to further normalize table into 3NF? The one on the bottom right.
To break it into two tables, instructor
break it down to more tables, right? To have instructor information in a separate table and only put instructor ID in the course, right? Just to link as a foreign key to link this table to an instructor table. So in each entity or each table, you only have attributes specific to that entity. And if that table or entity is related or connected to another table, then you have also another field, which is your foreign key, right? For example, in the course table, you only have course information like course ID, course title, course description, but you also have one more column that is related to another entity, instructor, which is a foreign key. Unless it's a foreign key, all others are just attributes of like the same entity. And yeah, so this is about like these three normal forms. So did you understand partial and transitive dependencies? Yeah.
For transitivity, do we have a case when we only have one primary key, or both columns should be primary?
No primary key. With transitive dependency, they are two non-primary key columns. So if you found dependency, like here, for example, between here, on the table on the bottom right, the red one, okay? So the red table here has course ID as the primary key, right? Course title, instructor name, and instructor location. Even if instructor name was instructor ID, which is a foreign key, right? Still, the dependency between instructor ID and instructor location is transitive dependency because it's between two. The dependency is between X and Y, which are non-primary key columns.
But then that's not a non-key attribute.
That's what I mentioned. When you read it online or in your textbook non-key, it means non-primary key. Foreign key, no problem. Okay?
I'm asking what if one is primary?
For example, course ID is a primary key, right? So what if you have a primary key, either your primary key is single or composite, right? If you have a single primary key, you don't bother with any partial or transitive dependency. First, partial dependency means a column depends on part of your primary key. So if your primary key is not a composite and it's only a single primary key, then there is no way of having a partial dependency. So you don't bother yourself with finding a partial dependency. Transitive is between two non-key columns. So if one column is primary key, that column cannot have a transitive dependency because it's a primary key, right? But in your table, you may still have transitive dependency between different other columns. Like for example here, the primary key is course ID, right? But there is a dependency between instructor name or instructor ID and location, right? Everyone agree on that? There is a dependency between instructor office, instructor location, and instructor ID or name? Anyone has question about that? Okay, so we agreed on that. So if that's the case, if there is a dependency between non-key columns, non-key can still be foreign key, okay? I mean non-primary key columns, then it's a transitive dependency, okay? So have a break for 15 minutes, 10 to 15 minutes. Okay? Yeah. I already included that in the course syllabus. I don't want to say the wrong date. You can find it on e-class under course schedule, and it's 1 week after the reading week. Not the exact right session, but one session later. No, I think should be the beginning of July.
In the first week of July.
I think so, yeah. Okay, everyone. So I would like to, sorry. Yeah, sorry. Okay, so in case just if you missed that, I updated the course schedule a couple of weeks ago, because I see students keep asking me about the midterm exam. So your midterm is scheduled for, I don't know the exact date, I think it's July 2, but it's not the week right after your summer break. but after that. So I can actually show you that. So here, so if you go to the course and course schedule, right? So you can see like this information here. So you have this session here on July 2 where your midterm exam is at that time, okay? And the reason is because I want to just finalize some of the concepts before we have the midterm. I would like you to have some time during the summer break to practice. And then the session after the summer break, which at first I wanted to have the midterm at that session, I changed my mind because I want to like maybe practice more with you before the midterm exam. So that session just not to, I don't want you to panic right after the summer break. Just giving you some time to get back on the track and then having the midterm here, July 2. And please try to attend the midterm exam because it's very difficult to accommodate you if you miss that exam. As much as I would love to help, but I couldn't find a way that is fair to all students who try their best to like make up for that test. Because what can I do? If I transfer the weight, the only way I can help is transfer the weight to the final exam if you miss the midterm. And the reason is because they are more similar in terms of the grading components, right? Rather than if I'm going to, for example, transfer the weight of your midterm to other components like assignments, that would not be fair to other students, right? So if you miss the exam, midterm, the weight will be transferred to final. And then your final will weight like something like 50 or 55%, which is a lot. So I would highly recommend you to attend the midterm exam. It's probably easier than your final. And it's a good way to practice to see the questions before. You study like in the middle of the semester and not putting everything for the end. And also breaking down you have two opportunities for the test, one midterm, one final, right? And the other thing about the office hours, so in case you don't know, to find the office hours, you can always go here, right? And I also asked the TAs to post an announcement before each office hour to make sure you don't miss them. But here is the schedule. So here you can see who is the TA assigned for each assignment. For example, assignment 1, 2 are marked by Dorsa. Assignment 3 is marked by Hakim. Then group project again is with Dorsa because he has more TA hours. Midterm and final, both. Okay? And so the office hours are also scheduled according to these components, right? For example, Dorsa will have office hours in the next upcoming weeks because she's the TA who is going to mark your assignment 1, assignment 2, and group project. So she's holding regular office hours weekly to help you with that. On top of that, I'm also offering weekly office hours on Thursdays, right? In case you have more questions. And online. All office hours are online so that students can join because it's easier for everyone to join online, right? And another thing, you can find also the time, the Zoom link and everything here. So you just have to make sure, for example, for Dorsa, it's not all Wednesdays. So you can find the days here, right? So these are the days that Dorsa will have office hours. And you can also find the days that Hakim will have office hours. But we will have at least 2 office hours every week, one by one TA, another one by me. Okay, that's the minimum that we'll have. Also, I added another component that is not graded. We are not going to mark it. It's just to give you feedback for your group project. So I added this here. So if you see here, I added a project progress report. So your progress report is just an optional component to give you an opportunity to receive feedback, early feedback on your group project, okay? Doesn't have any mark. You don't lose mark if you don't submit it, but you will get feedback from either me or the TA on your progress, okay? So if you have questions about your group project, that's a good opportunity, but you have to submit it by June 20, okay? And the feedback will be only on your design part because the limited time and also because that's the most important part of your project. If your design is going well, then other steps are like just you have to follow your ER model, right? And that's it. Just going back to give you one more example here. So for the normalization process, and more specifically for your assignment, because one of you asked me about like denormalizing, you may not need to denormalize tables for your assignment. It's just asking you to know that we don't always normalize tables, and I already explained that. But for this assignment, please just focus on the normalization. I don't want you to do the denormalization. You may want to keep a table intentionally in 2NF, for example, for some reason. Then you can explain why, okay? We'll see more examples today. And so please do not just write all tables are already in 3NF, so we didn't do anything. You have to further elaborate on that and explain why, for example, you want to keep a certain table in 3NF. How does it help, for example, later with the queries and everything, right? That's what distinguishes, for example, B plus from A from A plus, and so on. So for the normalization, you always start from the 1NF, right? First check if there are no duplicated rows, no duplicated, that is primary key should not be duplicated, right? And no multiple values in any cell. You cannot store multiple names in one cell, right? That's against the atomicity, and it means that the table is not 1NF. 2NF means table is already in 1NF and no partial dependency. How do you look for that? Check the primary key. If primary key is single, don't bother, it's already 2NF, right? If your primary key consists of more than one column, that's a composite primary key, then start searching for composite primary key. You may or may not have it. And then 3NF, just look for transitive dependencies. That is the dependency between non-primary key columns. For example, instructor, name, and office in a course or enrollment table, right? Now, look at this example. So we have this view, for example, from in a hospital context. We have date, patient code, patient name, procedure, and charge. Is this 1NF? If we create a table like this, is it first normal form? No. Why is that? Yeah, we have multiple values, for example, in procedure, in charge, right? So it's not 1NF. And here, so can we call it a relation? Can we call this table a relation? No, because, for example, for each doctor name, for example, Dr. Campbell, right, we stored several values for different attributes, right? Yeah. For example, here, for this doctor name, we have 2 rows of data, right? Again, for this one, we have 2 rows. It's more like a report, not a table, not a relation, right? And can you find the dependencies here? What are the dependencies?
Patient code and patient name.
Okay, patient code and patient name. So you have to say which one is dependent on which one. Can we say patient code depends on patient name? No. The opposite way, right? We can say patient code uniquely identify patient name, or patient name is dependent on patient code, right? That we can say. So there is a dependency between patient code and patient name. And What else? What are the other dependencies? Doctor name and specialty, right? Because each doctor have a specific specialty, right? By telling the doctor's name, you should be able to say the specialty. So here, now let's first look at the table on the right, okay, this table. We have visit ID, procedure, and charge. So which normal form is this table? I already had the answer here. You can just explain why. It's first normal form, right? We didn't store multiple values in a single cell, right? And your primary key is composite primary key, right? Visit ID alone is not a primary key here, it's duplicated, right? Procedure also. So we have a composite primary key. Can we have a partial dependency when we have a composite primary key?
Yes.
Yeah, we can. And do we have a partial dependency here?
Yes.
Between
Charge
charge and procedure. Great, exactly. So because each procedure has a specific price, right? For example, X-ray has some price. I don't know, chemotherapy has another price. So by telling the procedure name, you can identify the price. So there is a partial dependency between charge and procedure. And so it's not in 2NF, right? There is a partial dependency and it's not 2NF. Is it in 3NF? The table on the right? No 3NF because it's not in 2NF, right? If it's not in 2NF, you don't even bother with 3NF. Now the table on the left. So imagine the primary key is the visit ID, okay? In this table, visit ID is your primary key. So first of all, is this table in first normal form? Yes. We don't have any duplicated rows, right? We don't have multiple values stored in a cell. Just to let you know that, for example, the column specialty, the first row is internal medicine. That's just one value, okay? That's not duplicates. Or for example, patient name is Baker Mary. The best way to store that is first name, last name. But we are not dealing with perfect tables here, right? And so what are the dependencies? Now let's find the dependencies in the table on the left. So we said that it's 1NF, so we can move into 2NF. For a table to be in 2NF, there should be no partial dependency. For partial dependency, look at your primary key. If it's a single primary key, no partial dependency. Do we have a single primary key here? Yes. Visit ID alone is your primary key, single primary key. And there is no way of having partial dependency because partial dependency means you have one column here in your table that depends only on one part of your primary key. And our primary key doesn't have different parts, right? So no partial dependency, so the table is already in 2NF. We can move to 3NF, right? Means table is already in 2NF plus no transitive dependency. Transitive dependency is dependency between non-primary key columns, okay? So do we have transitive dependency here?
Yeah. Yes.
Yep. What is the transitive? What are the transitive dependencies? Yeah. Patient code and patient name. Patient code can uniquely identify patient name, right? And what else? Specialty and doctor name. By telling doctor name, you can find the specialty. And because each of like these columns are non-primary key, right? None of them are primary key, but there is a dependency. That's a transitive dependency. And when we have a transitive dependency, it means that the table is not in 3NF, right? So you may want to further normalize table into a 3NF table, right? Now, let's say we normalize table this way. So we have visit information here, like visit ID, doctor name, date, and patient code, right? And then we have one table for doctor and one table for patient. Can anyone explain how did I come up with these three tables from here? Like from here. So look at the table on the left. We have visit ID, doctor name, specialty, date, patient code, patient name. We already know that it's not in 3NF. And we know that there are two transitive dependencies, right? How do we normalize? Wherever you have a dependency, break that dependency and put it in another table, okay? So dependency 1 between doctor name and specialty, right? So it means we want that information in another table to get rid of this dependency in this table, right? The same way that we did it for the course, the student name in the enrollment table, right? We put the student name in the student table. We got rid of this information, student name, in the enrollment table so that the enrollment table could be in 3NF, right? The same way we do it here. We get rid of a specialty doctor name here. So if you look at this table, now we have a specialty and doctor name. We got rid of that, put it in another table, right? That's a doctor table. It may have more in columns, but here we just keep it simple, right? And what is the other transitive dependency that we have to get rid of? Patient information, right? Patient name and patient code. So we also want to have another table for the patient. So the only thing that we can keep in the visit table is actually doctor maybe ID or something like that, or patient code, right? Which serve as a foreign key if you want to know, for example, in each visit, who was the doctor, who was the patient, right? Yes? Am I clear? Have questions? Okay. So this is how we store. We have the doctor. It's better to have a doctor ID, okay, here. It's not perfect because even in the initial table, we didn't have doctor ID. But if you have a doctor ID and doctor name here, then please put visit ID, doctor ID, patient code, and date. That's the best way to design it. And then doctor ID, name, specialty in another table, patient ID, patient name, and other information in another table. And
I have one question.
yeah.
Like for example, suppose you have it's optional, like to create a separate entity or just put it as an attribute here.
Mm-hmm.
So if you create entities, like which is optional, is it economically inefficient?
It depends. Like if that attribute that you optionally want to create a table based on that or define it as an entity, you define it as an entity or another table only if you are going to query that specific table a lot. And you're going to have lots of, for example, updates, inserts, or even like just select a statement from that table. Otherwise, you don't do that. If that's a table you not frequently update or you don't have to deal with that data like a lot of times or frequently, then you just put it as an attribute. And why is that? Because every time that, for example, you select some data, let's say you have a table, big table with like thousands of rows and like hundreds of columns, right? So having that, like if you want some specific information about that specific attribute, then you are like retrieving a lot of data from that big table every time, right? Whereas if you put it in a separate table, right, you only query that. But if that's not very like common, because even a table itself has some space and like it's not efficient to just have an entity or a table for anything, that we are not going to even use that a lot. No problem. So what could be the primary key here in this table? So we have visit ID, procedure code, procedure name, and charge. Visit ID alone cannot be primary key, right? It's duplicated. Procedure code also has like duplicated data. Let's say visit ID and procedure code together. Are they unique?
Yes.
Yeah, they're unique. And so it's a composite primary key. So what could be the foreign key here? Procedure code, right? Because procedure code in the procedure table could be the primary key. So could be the foreign key here, right? Yeah.
So a composite primary key, like those who are included in the composite primary key, so we can still make it as a foreign key?
Composite primary keys.
One of them.
Yeah, like each part, especially if they were, like, for example, associative entities before, each of them are foreign keys actually, because they're, like, what is a foreign key? A key or attribute that connects two tables together, right? And if you remember, for example, here, right, in the enrollment table, we had a student ID as a foreign key, course ID as a foreign key, and both of them together as a composite primary key, right? But why student ID was a foreign key?
Because that is connected to student table.
Exactly. And why course ID is foreign key? Because it's connected to the course table. So whenever there is a link or connection between two tables, it means there is a foreign key in one of those tables. And where do we add foreign key? Which table? Let's say we have a one-to-many relationship. Like, for example, employee and department, right? They have one-to-many relationship if we assume that each employee can work in only one department, but each department can have many employees working in that department, right? That's a one-to-many relationship. And we want to see, for example, the department name for a specific employee, right? Or we want to get, for example, a list of employees for a specific department. So there should be a connection between employee table and department table. Do we agree on that? Yeah. So we need to connect the employee table with the department table. And if that's the case, there should be a foreign key, right? Where should I add the foreign key? Should I add the employee ID to the department table? Or should I add the department ID to the employee table?
I think the department ID to the employee table.
Why?
I need a second.
I can help you with that. So this is employee, right? And we have employee ID, name, maybe department ID as you suggested, right? This is the employee table. And then we have also department table here with department ID, department name, and maybe employee ID here. So these are the two possibilities, right? Either we have to add the employee ID here or add the department ID here. There is no other way to connect these two tables, right? Now, as you suggested, if we add department ID to the employee table is the correct way, right? Because there is a one-to-many relationship between employee, right, and department. So these have one-to-many. Each employee can work in only one department, right? And each department can have many employees working in that department. So that's a one-to-many relationship. Which part is the many side? Employee is the many side, right? One-to-many, right? This is the many side. We always add the foreign key to the many side. And why is that? Because if we add the department ID to the many side, which is the employee table, we have, for example, one employee, employee ID 1, and each employee, right? Each of these employees working in only one department, right? Department ID, I don't know, EECS, business, and so on. We cannot have an employee working in more than one department. For example, I'm working in the computer science department, right? I cannot work in another department at the same time. If that's the case, then that's a many-to-many relationship, and that's different, right? But if my assumption is that each employee can work only in one department, and there is a one-to-many relationship, we have to add the foreign key to the many side which is the employee table. And if we added employee ID here, the problem was that we have a department EECS, right? But we have a lot of employees in EECS department, so we cannot add it to this side. Because for each department, we have many employees. So one-to-many relationship, you add the foreign key to the many side. That clear? Okay. So that's about the foreign keys. And if there is a one-to-one relationship, you can add it anywhere you want, right? Because there is no problem. In both cases, for each instance in the first entity, you have one instance in the other one, because there is a one-to-one relationship. And if there is a many-to-many, we have an associative entity, right? Which convert it into two one-to-many. Like a student and course, they have many-to-many. We break it down into two one-to-many relationship. And again, we know how to deal with one-to-many, right? Adding a foreign key to the many side. For example, adding the course ID to the enrollment. Adding the student ID to the enrollment, right? That was the many side of the relationship. So it's good to think about like these, like each table that you see here, think about what is primary key, what is foreign key, what are the dependencies, how can you normalize it. And for example, this table now is in the third normal form. And here as well, for example, we have procedure code, procedure name, and charge. And there is no repeated groups, 1 and F, no partial dependency, and no transitive dependency. That means third normal form. And can you tell me what is the relationship between visit and procedure? In order to understand what is the relationship type, that is it one-to-one, one-to-many, or many-to-many relationship between visit and procedure, you have to ask yourself, for example, you have to think of it this way. For each instance in visit ID, or for each visit, right, how many procedures do we have, and vice versa? Each visit, does each visit belongs to only one procedure? Have one procedure? No. No, we have many. The other way, for one procedure, can we have one procedure in different visits? Many-to-many relationship, right? That's a many-to-many relationship. And so each visit can have multiple procedures for treatment, right? And then each procedure can also be used for multiple visits. So these are just some tips for you to help you. And this is not a complete ER model, just the parts that we covered. And again, some tips that I've already covered. For example, each entity must have a key in your ER model. Whenever you have many-to-many relationship, introduce associative entity. And if you have a multi-valued attribute like phone number, convert it to a separate table. Most of the time. And so, can anyone, we finished, but we covered everything that I wanted to cover about normalization and functional dependencies. But now my question is, why did we do all this normalization? Everyone should be able to answer this question now. Otherwise, I have to rethink my teaching philosophy. So, why did we do normalization? Yes?
Reduce redundancy.
Reduce redundancy. Can you further elaborate, or anyone further elaborate on that? Yeah?
It's easy to do thread operations.
It's easy?
To do thread operations.
Sorry.
Thread operation, thread, read, update, anything.
Yeah, exactly.
To avoid redundancy means there is no column that you don't need it.
Yeah, or it have some dependencies, right?
Simplify the tables so you don't have duplicated information.
Sorry?
So you don't have duplicated information.
So that we don't have duplicated information, right? We don't have duplicated information means we want to make it in one NF at least, right? We want to get rid of the dependencies, right? Because we said that what are the problems? We actually repeated it in several sessions. From like 2 sessions ago, I was explaining why we don't put like all the information into one table, right? What is the problem, for example, if you put all the instructor, course, and student information in one table? So then there are insertion problem later, right? We have insertion anomalies, we have update anomalies. What if, for example, you want to update a specific, for example, information about the instructor or the course? Then you have to like access a lot of rows, right? So there are like all these problems. And denormalization, just a quick note about why we do sometimes denormalizing tables. So mostly, like basically what we've covered so far was about like transactional databases or OLTP applications, or when we have a database which is frequently accessed, or for example, written, updated, and so on. But sometimes you don't want that. Sometimes you may want to keep historical information. Maybe, for example, there was a price of a product when you purchased it, right? And the price was updated later, but you want to have that original price still. Sometimes we have, when we talk about data warehouses in the last part of this actually course, we learned that we want to actually have increase like the reading performance is more important for us. And we don't have much update on the current data or like insert or like anything like that. And if that's the case, it means why do we need normalization, right? Because we said we normalize because of like these insertion anomalies, update anomalies, and so on. But if we have a database that we don't need to, we don't have that much frequent update or insert and so on, and then we just want it for like analytical purpose. So it's easier to actually denormalize a table because then we have everything in one table, right? Then instead of joining many tables, because what happens when you normalize tables? You break one big table into different tables. So when you query later, you are accessing, in order to see, for example, enrollment information with the course names and the student names, you have to access 3 tables, right? You need a student table to get a student name. You need course table to get the course name, and you need the enrollment table to get the enrollment table. So later when we learn join, you need to do join between 3 tables. And when your table's getting large, like you have millions of rows and so on, that join taking like a long time and it's not efficient. So sometimes if you're doing like these frequent joins and you just want to do like data for like analytical purposes and they are not a lot of write on your database, then you may want to keep them like not normalize at least until 3NF. You may want to keep it until 2NF, right? Because in that 2NF form, maybe is what you need to access a lot. For example, maybe I want student name in the enrollment, so I keep it in 2NF. I normalize only until 2NF and not more. So it really depends on your goals. And that is what I want you to explain in your project, in your assignment. And I added some notes. I'm going to update it in your slide. You don't have these 2, but because a lot of students ask me, and I've seen a lot of issues in the past with designing a credit card. It's not about the normalization anymore. It's just a point about your assignment and project, because I've seen many students put credit card information in the customer table or in the order table. So not only is not efficient, it's not also a secure way of storing credit card information. So for credit card information, you may want having a separate entity, right, only to store card information, and that's also tokenized card number in that, right? And then you may also have another table for payment. So they are like 2 different things, because you may have different payment methods, right? And you may want to have a payment information table. You may want to have a separate table for keeping like just credit card information, and then order table, and so on. Clear? Okay. So, would you like to have a quick Kahoot today, right now, or would you prefer to do it at the beginning of the next session? Beginning of the next session, hands up. Yeah, you're tired. Okay, good. Have a question? No? Okay, thank you.